I will manage to explain to you and introduce you to blockchain technology as much as possible. It's going to be, I think, useful, but I hope it will be useful. However, I would gladly and cordially ask you that since we are only 8 in the room, this virtual room, that we make it as friendly as possible. Please think of me not like a classical lecture, because you will be shocked what I'm gonna also draw on the blackboard, and my writing is not really nice. I will also show you some slides, but on purpose switch between presentations here and there. So also try yourself to be as much cordially as possible. Stop me, ask me questions. It's going to be easier for me that I know where do you stand, do you follow me, and it's also going to be better for you, of course. And before I start, again, my name is Mohamed Turkanovic. As Dr. Konechna explained all about me, I'm not going to introduce more about myself. However, I would like to know more about you, because it's going to be also easier for me to know who am I presenting this. And as one of the ways to introduce ourselves, I don't need to know your names and surnames, I see them, but it would be nice to know what is your level of understanding blockchain technology, cryptography, and similar things. So I would kindly ask you if we do like 3 minutes brainstorming, and when I say blockchain, I'm gonna say, please tell me any word that pops up in your mind when you hear that word. Okay, so first word is, of course, blockchain. So can anybody tell me what's the first word they think about when they hear blockchain? So Zdenka, I'm not sure. Can they answer? They probably.
Yes, I have heard your question. Thank you very much. It's a very interesting question. So I would just like to start in the round by saying you that one of the first words that I would think about when I would hear about the this topic, blockchain, is no middleman, for example.
No middleman, exactly, and very, very helpful. Thank you very much. Anything else? Anybody else? You don't have to be shy. Or let's try this involvement of the public. Please raise your virtual hand, since you can use that using Microsoft Teams by raising your hand like I did right now. Please raise your hand, all of those who know, who thought about cryptocurrencies when they heard about blockchain. Okay, Margareta, thank you. Luhan, Jan. Okay, 2 of those. Good. Very nice. Okay, so I'm gonna start, and I'm trying to be as much as informative as possible, not to lose you too much with details. So I'm gonna try to explain you a little bit about blockchain technology and about verifiable credentials. And at the end of the session, I will show you an example of how blockchain technology can be used. And I will show you this on the principles of the EduCTX project, which is a blockchain-based platform for micro-credentials, which, however, also Brno University is part of. So as an introduction, why blockchain was very popular in the 2017 and maybe.
For interrupting, can you just make your slides a little bit bigger so we can see it? And yes, perfect. Thank you very much.
No problem. So blockchain technology was in 2016-17 meant to be used to be called the second internet revolution. It was used to be called virtual gold rush. And one of the things what blockchain technology was also coined by was representing the most important innovation in the field of internet technologies in ICT in the last decade in computer science. Some of these, of course, are true. The majority of these statements are not. But one of those statements is also that the blockchain technology is surely the basis for new concepts. And these new concepts will surely and are already changing established business processes. Many companies currently, also Fortune 500 companies, are introducing blockchain technology in their services, in their business, be it with the right intention or the wrong, be it implementing it on the using the right tools and frameworks or not. We will discuss about a little bit about later on. Just as a short introduction, in 2015, I hope you know all about Gartner, the institute, IT consulting company, a global IT consulting company. They are making every year these hype cycles for emerging technologies. And as you see, in 2015, Gartner, the biggest IT consulting company in the world, didn't mention blockchain technology at that time in their hype cycle, and that's their job. It's their job to find innovative technologies. And in 2015, nobody, not even Gartner, talked about blockchain. However, they first introduced cryptocurrencies, as you see on the curve somewhere here. So even at that time, 2015, Gartner didn't talk about blockchain technology, but they were talking about cryptocurrencies like all other people who were not involved in that. However, in 2016, Gartner changed their mind and introduced blockchain as the technology and skipped actually the cryptocurrencies, because as they realized that cryptocurrencies are not the technology, cryptocurrencies are just an application of the blockchain technology. In 2017, we see that blockchain technology has gone over the hype cycle and started to develop towards the truth of the delusionment, and we are hoping to see the blockchain technology more on the slope of enlightenment in these years and on the plateau of productivity soon, but it's also not so happily as it is. Also in 2017, 2018, also in 2019 and 20, Gartner coined 10 strategic technologies which should not be neglected by companies. And in all these years, already now the fourth or even the fifth year, I think, Gartner never skipped blockchain technology as one of those technologies the companies should not neglect and should be very careful of. So if I go now to the fundamentals of blockchain technology, if we want to understand what blockchain is, we should really understand what the core concepts of blockchain are. And we skipped and we introduced the blockchain technology. We introduced blockchain technology at our laboratory by explaining three important parts. First of all, you need to understand cryptography, because blockchain is really based on cryptography. Second of all, you need to understand databases, because a ledger is nothing else than a database. It's just a distributed database. And you need to understand the concept, of course, of peer-to-peer network, because we have a network of peers. We do not have a network of a master-slave architecture. And we have these so-called distributed consensus algorithm, like the proof of work or the mining, as a lot of people talk about them. So just to make a short introduction about security principles and cryptography, what cryptography in general is, it's the science and art of designing codes and protocols that aim to change plain text into cipher, etc. So the idea is that we disable unauthorized people to read something that we do not want them to read. However, we still want to be able to share this information in a public manner. And we also want that only the person who the message was intended to can read the message and nobody else. And cryptography, of course, introduces concepts like encryption and decryption, etc. And today we use cryptography just like microwaves. We put the food in the microwave, we get out of the one microwave food, and nobody thinks about how it actually, how the food and our sausages and our soups got warmer in the microwave. We just eat it. And as the same principle applies for cryptography. You use it and we use it every day in all of our private or let's say professional work, be it using online banking, using through Microsoft Teams, etc., to WhatsApp and other applications. We use it daily using also our emails if you digitally sign them, encrypt them, etc. But we don't even know anymore how it's working. We just say, okay, we are safe using the internet. And that's also one part that's for the layman also enough. Just a small explanation why this is important. We divide, not we, well, the professional and scientific community divide cryptography into symmetric cryptography and asymmetric cryptography. The asymmetric cryptography, the right one, is also called the public key cryptography, and I'm going to explain you about why. But first of all, let's talk slightly about symmetric cryptography. What symmetric cryptography actually stands for is that it stands for symmetrics. So it means that if you have one password, if you have one key, you will use this one key to let's say hide something, and you will use this password and key to unhide it. Or in more professional way, we use one key to encrypt something and use the same or equal key to decrypt it. And asymmetric cryptography, introduced in 1960s, introduced the concept of public key cryptography. Here we have a slightly different idea, and this idea changed the digital world that we know today. In this asymmetric cryptography, which is the basis of everything you know actually already today, is that every person should have a private public key. And as you see here, we have Alice. Alice has a private key. I have denoted it with the red color, and her public key, which is in blue color. These public-private keys, they are linked together. And if you know anything about physics, you should know about entangled photons or entangled, let's say, nano atoms. In this case, you see that you have two different atoms. They can be on different spaces in the universe, and however they are entangled and they are connected together. In the same way, these private and public keys, you and me, are connected together, because in mathematical form we actually first create the private key and we calculate the public key from the private key. That's why they are connected together. But why is this important? Let's see why this is important. Let's say that Alice, in this case, because she's in love with somebody and she loves Martin. And since girls, at least in Slovenia, and at least when I was young, they wanted to be more open-minded, and whenever a girl was in love with you, she would actually tell that to everybody, and girls were more open-minded about love. We boys were shy. We didn't want it to nobody should know about who am I in love with, and not even the person who I'm in love with, etc., etc. So the idea in this case is that how could Alice, if she is in love with Martin, and in the times of Corona, where she's not allowed to go outside, at least in Slovenia, we are not from yesterday allowed to go outside from 10:21 o'clock, how can she explain to everybody in the world, post it on Facebook and say, I love Martin and everybody should know that? How can she do that? Well, if we know about asymmetric cryptography, we know that Alice created her public-private key pair. It's a key pair. And what she can do is, she can use the red key. And one thing that I didn't mention, and you should probably already know, is that the red key is totally private, like the name itself mentions. The private key shouldn't be exchanged to anybody. It should be totally secretly kept. However, the public key is something that Alice can broadcast over the radio, post it on Facebook, wherever she wants. Okay, so what can she do with these two keys? Well, she can write down a note, I or Alice loves Martin. She can use her red key. With this key, she can encrypt this message, Alice loves Martin. And when she encrypts this message, I hope you can see now I'm gonna just use something. Yeah. So, okay, so, and as you can see here, she made a text, encrypted it with this red key, and now she gets something like this, something nobody can read, okay? Nobody can read this. However, what she does, she can now post this thing on the Facebook, Okay, she can post this thing on Facebook and write down, well, people, it's me, and I'm telling to the world I love Martin. And she will write down this message, and beside this message, she will also write down Alice loves Martin. So everybody in Facebook will be able to read this. However, everybody will be curious what to do with this thing. Well, this thing helps all of us to identify that this message was really written by Alice. Why? Because if something was encrypted with this key, encrypted, it can be only decrypted if you use the blue key. If you would encrypt something with the blue key, you could decrypt it only with the red key, okay? However, since we all know that Alice's red key is only kept with herself privately, and we decrypt it with her blue key because we all know about her blue key, it's publicly available, and we get again the same message as at the beginning, we can be sure that only Alice was the person who was able to write or encrypt something like this. Okay, so in this case, she used this key pair, the red and blue, private and public, to digitally sign something. And this is a concept where we use cryptography to digitally sign a message. Why is this important for blockchain? Well, because whenever you publish a transaction, or in this case, I'm gonna explain to you in cryptocurrencies because that's the most prominent word in blockchain technology. When you spend your Bitcoins, well, you have to digitally sign them that everybody else knows that it was you really who spent that. Because if it wasn't you who signed that, then nobody would actually accept these cryptocurrencies. Okay, so if we go now on and say we are still on the asymmetric cryptography, and please note now that here is Martin, and you're probably astonished why she was in love with him because he has no hair, but she is, well, we don't know why. However, what we know is that even Martin has his own private public keys. And please be careful that Martin's private key is denoted as with the green color. Martin's public key is denoted with the, let's say, grayish or brownish color, whatever. And now Martin wants to reply to Alice, well, I'm also in love with you, but since he's a boy, as I said previously, he doesn't want that everybody knows that. What he wants is that only he is able to send her this message, but he wants to ensure that nobody else can read this message except her. Because Martin is like, let's say he's a Casanova. He has 2 other girlfriends and he's sending them the same message, okay? Something that pretty much happens in real life. So what does Martin do? Well, he creates this message, I love you too, and encrypts this message. But please be careful. What does Martin do? Martin encrypts this message using Alice's public key. You see, it's the blue key, and this blue key belongs to Alice. But everybody knows Alice's public key. Well, Martin has now used the blue key, encrypted this message, and now we get something like this. Well, the problem is nobody can read this message. Well, nobody except then Alice, because if Alice uses the other key now, the red key, for decrypting the message, she and only she will be able to decrypt it and read, I love you too. Well, Martin is a smart guy and he found a way to show only to Alice that he loves her and nobody else will be able to read that. But there is a problem. Does anybody know what the problem is? Or is anybody listening to another question? The question now which I am raising is, in this scenario, on this slide, can Alice be sure that the message which was sent to her was produced by Martin?
No, she cannot.
No, she cannot, because
the blue key is publicly available.
That's right. Blue key is publicly available, and you could do it, or I could write down I love you too and send it to Alice. and she would encrypt it. Only she could be able to do that, but she would not be able to be sure that Martin sent that, because I could make up an email, martin@gmail.com, and send it to her. How can she be sure? Well, she could be sure that Martin sent her that if Martin would use this encrypted message, encrypt it with his private key, and then send it to Alice. Well, if Alice wanted to get the message out, she would first have to use his public key. When she encrypts this, she would then use her private key to encrypt the message, and she will read the message and also be sure that only Martin was the guy who sent her this and nobody else. So in this case, we would use the asymmetric cryptography for digitally signing something and also for encryption. And we are using this all over. Okay, so this is asymmetric cryptography, and asymmetric cryptography is the basis for RSA. And RSA is actually River Shamir Aldemar. It's the core basis of, for example, all the cryptography we are actually using when you're online banking. HTTPS protocols are based on RSA protocols, etc. Why I'm telling you this? Because in blockchain.
Sorry.
Yes.
Can I ask the question? Just to the last step, I just try to understand if Martin's public key is also available because it's public for everybody. How can, and Alice is using this public key to read Martin's message, how can they be sure that not another person than Alice is decrypting the message? You know what I mean? It's like the other way, just the same problem on the other side.
Yeah, well, I'm going to show you, I'm going to try to explain you again. I hope you see this. Well, first, Martin writes down, I love you, Martin. Well, however, this is a text file. Martin will first of all use Alice's public key of Alice. Okay, this way he ensures that nobody else can read this message except then Alice, because she will have to decrypt it with her private key. But he does not send her this file. What he does is he uses again this one. He encrypts this file, the already encrypted file with public key of Alice, with his private key.
Okay, it's already encrypted.
The already encrypted file. So what Alice has to do is, to open the first box, she has to use his public key. Okay? Public
and
key.
Then the private one.
And then her private one. In this case, she knows that it was received by him, and she knows only she can read it. Okay, so it's a double package. It's like those matryoshkas. Yeah, it's like those Russian matryoshkas. You open one box and there is a smaller doll in it, and smaller doll, etc. Okay, so I guess you understood. No. I like the aha effect. Okay, so these cryptographies, they're all in today's basic world that we live in. They are based on RSA. So HTTPS protocols, like I said, your online banking, they're all based on RSA cryptography. And let's say the National Security Agency of the United States of America, it's the, let's say, probably the most sophisticated computer cybersecurity core institution in the world. Well, they say that the top security files of the United States of America, they should be currently encrypted with 3072-bit keys RSA, and it's totally top secret. Okay, if you want to encourage even more security, you would use even bigger keys, for example, okay, etc. Even more. But the problem is, the way you increase the keys, the calculations get slower, etc. Why am I telling you this? I'm telling you this because in blockchain, when blockchain was introduced by this guy, Satoshi Nakamoto, whoever he was, he introduced elliptic curve cryptographies in their calculations. So in blockchain, you have the same principles, these keys, blue, red, etc. But in the core level, they are not implementing using RSA, but they are implementing using elliptic curve cryptography. Why? I'm going to tell you that a few steps later on. Another thing that we should note is in blockchains are based on hash functions. What are hash functions? To be short as possible, a hash function has two main features. The first feature is shown in this, and also the second. But let's say a hash function is a function where you put an x in it and you produce an. Okay, in this case, this world hello is the x, and this box here is the epsilon. Okay, so the thing is that these hash functions, they enable you to input any x that you want, but the thing is that even if you put a slightly bigger x in it, you will always produce the same length. You see, even if I put the Slovenian anthem, this is the Slovenian anthem from France Prešeren, and if you put this into the x, you will always produce the same length, not the same content, but the same length. And this length will always be, in this case of SHA-265, it will always be 256 bits, 200 bits, okay? The output is always the same. Input can be differently, the output is the same in length. However, the content will be always different, and the content will always be random. So you cannot be sure, and you will never know, and you can never anticipate what the output will be because it's totally random for some input. Okay, an example. Probably you read Tolstoy's War and Peace. Well, I read it only 60 pages and I stopped, and I never read it, okay, until the end. Well, if you are the same as I am, here, please read this out loud, and you can say to everybody that you have read the Tolstoy's War and Peace book. Why? Because literally I have used the txt file of Tolstoy's War and Peace, put it into the SHA-256 hash function, and this function has produced me with this output. Okay? And that's it. What is to note is something else. So not only does the hash function output some random string, and with always the same length, there's another catch. Let's say I open the book on page 515, and on this page I remove one dot, I remove one comma, or even I remove just one black space or one character. Only on page 515 the book will be the same. The thing is, when I execute the hash function again, well, the output will again be of the same length, but the output would also be totally randomly and totally different again than the previous. It may be something like this. Okay, it's not just that at the end you will have B except from A. No, it's totally different. Okay, why am I telling you this? Since you're listening to something about blockchain, well, every time a blockchain transaction is produced, the blockchain transaction is also hashed. And that's the core principle of blockchain. We could say that the core principle of blockchain is not actually a ledger, it's actually the hash function, okay? But of course, it's also the ledger. So that's about cryptography, some basic introduction into it. Let's go to the distributed database. So what are distributed databases? Well, in many cases, since probably, I don't know if you're computer science background or not, Nevertheless, I'm going to explain you some basics. Let's say we have an app. This app can be your smartphone app, your university's webpage, doesn't matter which. Well, users, they will go to this app and they will get some return. They will use a login, register, buy, whatever. However, this app is connected to one database, okay? One database. Doesn't matter which database this is. Is it a NoSQL, MySQL, Oracle? Doesn't matter. The thing is that these, in pretty much many words, are monoliths in 50% of cases, meaning they are there's one server. On this one server, you will find one application and one big database. And if you have 1,000 users, all of these users will be connected to this one server and to this one database. Well, the problem is if you are Amazon, or if you are Booking.com, or if you're Airbnb or Uber, you cannot afford to have only one server with one database, because then you don't have one guy who is using your app. Well, you have millions of people. I'm not going to even try to draw that, okay? Millions and millions of people accessing your database and accessing your app, and of course your database. And in this case, your database cannot cope with that, and it starts to go slow or crashes, etc. So what the thing is that it's already, we know these concepts for 30 or even more years. What people are doing is that they are distributing their databases. Well, in this case, you don't have only one app. Well, you have one app, but you are distributing this app on multiple servers. This is server 1, this is server 3, this is server 4 or 3, whatever. And each of them has its own database, okay? Now, previously, you had one database. You still have one database, but now it's replicated. It's duplicated on various computers. What helps you is that now, let's say 200,000 people can now connect to one server, 200,000 people can connect to the other server. In this case, you're balancing the load between various servers. And this is called scaling out. Okay, I'm not gonna even talk about scaling up, okay? But the thing is, in distributed databases, what we say is you can replicate the database. A replication means that if you have one database and you have 100% of this in one way, and you replicate it in 3 servers, well, the replication means that you still have the same database and it still is 100% the same. What you're doing is, today politically we are not anymore allowed to use these words, but still, master, slave, you will probably heard it in this form, master and slave, okay? Well, if somebody puts something into the master database, this master database replicates this information to other databases. And now you have users, and these users, they can read either from this, or this database. You're actually distributing your database. Why is this important when I talk about blockchain? Well, a blockchain ledger is a distributed database. However, data in the distributed database of a blockchain ledger is not stored in tables. It's stored in a so-called ledger. It's appended data with hash information in it, probably, okay? So that's the core principle that you need to understand about why distributed databases are necessary. If anybody has the question, as you see, I'm doing this really fast because I don't know your background. If I'm too fast, if I'm too slow, please just raise questions as the previous attendee also was brave to ask. If not, I'm gonna continue with my presentation. Okay, so the third concept that we need to understand are peer-to-peer networks. Can anybody tell me what comes to their mind when I say peer-to-peer network? What's the first thing what they think of?
Yeah, as I just said in the beginning, no middleman. So it's on the same level, so to say. There are no participants that have more rights, so to say, than the others.
That's great.
I would put it like this.
Yeah, middleman. And if I would go back to the previous slides, here we have actually the middleman. Why? Because we have the master and he's the middleman in this case. If you want to say something to the, in this case, slaves, you cannot tell them directly. You have to tell to the master and the master will tell it to the slave, okay? And in this case, when you have a peer-to-peer network, there is no master, there is no central authority. Every computer, every server in this case is the master, and every computer in this sense is also the slave. I don't know how familiar you are with NoSQL databases Cassandra, which was introduced by Facebook in 2015. Well, Cassandra is a NoSQL database, Cassandra NoSQL database, okay? Well, in Cassandra, it's a distributed database, and you have a distributed database, let's say, on 4 or 5 computers. And now your user, and these computers are all interconnected with each other, okay? And now your users, they can either connect to server 1 or server 4 or server 3 or the database, in this case Cassandra at server 3, etc. It doesn't matter. You can store data at any of these servers, because when, for example, you store one data at server 4, well, server 4 will store this data, and because of the replication factor, send this data to all others. And when somebody puts data at server 2, the same will apply to others, okay? And Cassandra is a principle of a peer-to-peer network, which on the top of it, at the data level, you have a distributed database, in this case, a NoSQL database. So why are peer-to-peer networks for blockchain important? Because you don't have a middleman. You don't have one guy, one central point, which dictates how the logic will be executed. Okay, so I will at the end also, I don't know if will have time, also talk about a little bit about IPFS, because we introduced IPFS also, sorry, we tried to use also IPFS in our EduCTX solution, so I will come to that at the end. So let's talk about now blockchain. We introduced the technology, the principles, and the course, as I said, well, Bitcoins are something, cryptocurrency, blockchain is that what we are talking about. And at the end, I will also show you how we use blockchain technology to store students' diplomas on the blockchain itself. Okay, so before I also continue, a point about peer-to-peer networks. Well, we know about various types of networks. We know that computers can be connected to a centralized network. Okay, and in the centralized network, you have one computer, the master, and the master tells to the other computers who are connected, and this can be a LAN, this can be any type of Ethernet network, for example, computers connected to each other. But this one server from the administrator, he dictates the protocols, he dictates what they will do, etc. But in a decentralized and distributed manner, and there's a difference in distributed and decentralized. In distributed, we say that we distribute the data, we distribute the traffic, we distribute everything that we have. And decentralized also means that when a system is decentralized and distributed, means that we now distribute all resources between these computers. However, none of these computers have any more privilege than the other. They're totally decentralized. Okay, they can only vote by majority if they want to change something. Okay, so when we talk about blockchains are distributed and decentralized. Distributed in manner because they are sharing data like a distributed database, and decentralized in the manner because no computer in this peer-to-peer network has more privilege to say and dictate than any other. Okay, so to introduce you why blockchain is important and why it's interesting, I will try to explain it with you on this manner. Let's make a mind game. Let's make a mind game, and let's say in the physical world, okay, we are not able to do that, since I would already be in Brno with you guys, but because of the coronavirus, we are not allowed to do that in this case, okay? But if I would be there, I would now open my wallet, pick up the €5 banknote, and I will actually be able to give it to you. Well, why is this important? We never think about that, but it's really funny that we do not think about that. Let's say I have this €5 banknote and it's physically in my hand. When I now use it and give it to you, okay, it's virtually out of my hand, okay? I cannot use it anymore. I gave it to you. I can only beg you to give it back to me. I'm not physically in the hands of that. Okay, so let's say that because of the coronavirus, I'm not able to send you this information, and I want to use the virtual means, Microsoft Teams, emails, etc. However, I'm not trusting the banks to do that, and I want to implement something by my own. Okay, so I'll try to implement something by my own. So I will do this. Well, create a TXT file. Okay, a TXT file, and I will write in the TXT file, I, Mohammed, send any one of you, for example, or I, Alice, in this case, send Martin one digital value. Okay, this is a TXT file. I create a TXT file. What Alice now does is she uses her private key, as you remember, the red one, and she gets this. Well, now what happened? By doing this, Martin will know when he opens this message with her blue key, and the blue key is available to everybody, that only she was able to do this. And because only she was able to do this, well, he knows that she spent her one digital value, one digital euro, let's say. Well, the problem, we have one challenge. If somebody intercepts this message, okay, well, this message can be copied and sent multiple times. Or she can even send the same encrypted TXT file to Martin and to you and to me. Okay, she would in this case be actually printing money. So how do we solve this problem? Well, we solve this problem by updating the protocol. And we say, well, if you want to do this, Alice, you will have to write down such a message. I, Alice, send Martin one digital value with such an ID. Well, what did we gain with this? Well, if she encrypts this with her red key and sends this to us, well, using her blue key, we will be able to decrypt it and read the message. Oh, but if she sends this again to us, if she tries to print money and send a duplicate of this message again to us or to anybody else, well, if you get 2 such messages or 3 such messages from her, when you decrypt it, you will read 2 times the same ID. And in this case, you will see, well, okay, maybe she did it not on purpose, but she sent me the same value. So I will neglect the 2. I will accept only 1 because I can have only 1 ID. Okay, but the problem is, how does Martin even know that this digital value 851321 really exists? Well, in our world, the banks do this. And if you remember, when you look on your banknotes, €5 banknotes, here somewhere you will see some IDs, okay? Each banknote has its own unique key. And these unique keys are enabling or disabling people to actually just copy it. Because even if you're so perfect to copy it, you will have then on the market 2 €5 banknotes with the same ID. But since we do not want to use banks, how can we ensure that Alice and Martin don't come up with some duplicates and some IDs which doesn't matter? So what we do, we can only distribute, and we can only use something that we can use already. And these are distributed machines and distributed systems. So let's say we have a group of these people, okay? And now what the protocols defines is that Alice will write again the same TXT file where she will say, I, Alice, send Martin one digital value with such ID. She encrypts this file, sends this file to Martin. But what does Martin now do? Look, Martin now opens the message, reads the message, and now Martin sends the same message to all other friends in the network, to the peers. This is a peer-to-peer network, meaning no one in this group has more power above the other than anybody else. Everybody is the master and everybody is the slave. Okay, so what's the purpose of resending the message to everybody else? Well, the purpose is that, as you see here, everybody, each one of them has a note, a database, a piece of paper. And when Martin sends them this message, well, they all write down the same thing. I'm gonna write it only once, okay? But they do the same thing. They say that Alice sent Martin one digital value with the ID 51321. And if Alice would do the same thing and send, let's say hypothetically, that Alice would send the same file to this guy, well, he would send then this message to everybody else. And everybody else would try to write down Alice has sent to John one digital value with 851321. Well, at this point, they will realize that something is wrong, that this ID was already used and that this ID is now with Martin and not anymore with Alice. And they see that Alice is a fraudulent person, okay? But we still have one problem, okay? And the problem is this one. Let's say that Alice now, and this is actually solving the double spending problem, what cryptocurrencies do very good. We see now that Alice writes down two messages. In one message, she writes down, I, Alice, send John one digital value with this ID. And in the other text file, she writes down, I, Alice, send Martin one digital value with such an ID. Okay? She encrypts these two files, prepares two emails, and at the same time clicks send to send. Well, now two emails were sent at the same time, and they were received by John and Martin in approximately the same time. Well, no problem, right? Well, here comes the problem. John doesn't have a problem, Martin doesn't have a problem, but now John sends this information and Martin sends this information to this girl. Well, she now receives two messages. In two times she reads, Alice sends this ID to John and Alice sends this ID to Martin. She can either say, okay, I'm not accepting any one of those because Alice is cheating, or she can say, well, I'm accepting first the one of John because he sent me the message first and I'm neglecting the one of Martin. Well, if she accepts from John and neglects from Martin, well, everybody else should do probably the same thing because the system will break down. But if she wants to enforce the others to do that, well, she doesn't have any power because it's a peer-to-peer network. So we found a solution how to prevent double spending in the virtual world, but we have a problem because we are in a distributed sphere where there's no boss in it. It's a peer-to-peer network. Well, how can we ensure in such a distributed network that then at the end we have one truth? Okay, and we need a system to solve this. Well, we have a system, and the system is distributed consensus. And distributed consensuses are something that are nothing new. We know them from the Middle Ages, okay? But the idea of the distributed consensus implemented in the IT sphere is an algorithm, a distributed consensus algorithm. And this distributed consensus algorithm ensures that it establishes trust among stakeholders in a peer-to-peer distributed and decentralized network. So how does this function? Well, we call distributed consensus also mining, and we have various consensus mechanisms. The most prominent one is proof of work, and this is mining. Okay, but we have also proof of stake, proof of authority, proof of time. And please note that we have also these. However, I will explain to you what mining is, that you will understand why this is important. Okay, so what is a proof of work? And I will try to explain you again with a mind game. So let's say how does proof of work actually functioning? We are in the 1830s. In the 1830s, we don't have any computers. We don't have any communication devices. We have banks. We have these safes, or how do we say them? We have a clerk who works at the bank, and we have customers. Well, the customers come to the clerk. They want a loan. They want they put some money in it. However, they produce these transactions. This is a transaction. Okay. So the bank in the 1830s doesn't have any databases to store the values. And let's say here's a transaction where Alice borrowed 500 gold coins, okay, in the 1830s. Okay, well, if bank gave Alice these 500 coins and she went, and the only guarantee that the bank will get these 500 coins back is this note, paper note, which they all signed. However, since this paper note, if it's in the bank, well, the bank can burn. And if the bank burns, the paper burns. And if the paper burns, nobody will remember that they gave Alice these 500 coins. So what can they do? Okay, well, the bank comes with a solution. They prepare a top secret house. Okay, top secret house. It's somewhere in the woods. Okay, this is somewhere in the woods. Nobody knows where it is. Okay, and they lock this room in this house, and nobody can come in it. However, they employ this student. Okay, and at least in Slovenia, students work for very cheap, and they do a lot of things just to survive. Okay, and the bank exploits this. Okay, now what the bank does is it employs a student, and it tells to the student, look, we will bring you daily checks, transactions. What you have to do is you will have to store these checks into a box. Okay, these checks need to be stored secretly in a box to avoid burning, stealing, etc. However, since a bank is quite, let's say, structured, they want that everything is categorized, and they want that each box is the same weight, same length, etc. So it's going to be easier for them to search. So they give some instructions to the students. So what they say to the students, look, we will give you some weight. It's so precise that it will measure the weight of these transactions in these pieces of paper on milligrams. Okay, what you have to do is please put these checks and these transactions on the weight before you put these transactions into the box. But however, you're not allowed to put these transactions into the box before you come to 1.000 milligrams. Well, the student didn't think it true when he said, yes, I will do that. And he went into the cabin. What he has done is he put 3 transactions on the weight, and he came to the weight of 0.709. Well, if he puts another transaction on the weight, he will produce, well, 1.1. Okay, so this is not the right one. He will use another one. But if he puts another one, he comes to 0.999. Again, not the same. Well, he will try to use another one. Well, the problem is, whenever he comes to another check, he never comes to the 1.0000 milligrams. And he calls the bank and tells them, well, are you sure you want to this? This is not possible. And they tell to him, yes, of course, but you didn't listen. In the corner, please look back. You will find a grain of sand. Okay? Well, yes, and what should I do now? And they tell him, you should put so many checks on the weight until it's stopped. You cannot put any more. And when you have so many, as much as they go, you will put your hand into the sandbox and try to put so many grains onto the weight, sand grains, until you come to the solution at 1.0001. If you could come to this solution, what you will have to do is you will put these transactions into the box. You will create one sheet of paper, and on this sheet of paper you will write down which transactions did you put into the box. And he writes down 1, 2, 3, 4, 5, 1022, 10101, and he writes down 4 sand grains. Okay, this is his job, and he does that. You see, this is this sheet of paper, this is this information, and he writes down this 4 sands of grain, and he puts this paper on the box. Why is this needed? Because when the clerk comes and wants to find some transactions, he will not have to open all the boxes. There will be a sheet of paper on the box, and there will be information which transaction is which one. However, now the student has this one box. Okay, and he's not finished, because in the meantime the bank brought additional transaction because he was so slow. Okay, and because he was so slow, he has now to do. However, the bank didn't tell him that he has to do it FIFO, first in, first out. Well, he has to do just bag the boxes. Well, he uses one box, one check, another check, puts 7 grains of sand onto the weight and comes to the solution. Well, now he repeats the same thing. Opens another box, box number 2, puts the grains of sand in it, puts the checks in it, takes a paper, writes down which checks are in the box, and writes down the number 7 because 7 grains of sands were necessary. And he also copies the previous label from the previous box onto this sheet, and puts this sheet of paper onto the box, and now he has already 2 boxes. And when the clerk comes, he can read this sheet of paper and know what's in this box, and in the same sheet of paper he will also know what's in the previous box, and the student continues. Okay, well, pretty much similar, right? But at some point of time the student comes to his mind and tells himself, but I'm working as a horse 20 hours a day and never get a correct salary. I work for 1 hour for €1 an hour, and it's exhausting. And he thinks, well, nobody sees what am I doing. Nobody controls what I'm doing. So what the student does is he takes one check, and if one check says that Alice has sent Martin 500 coins, well, he will delete Martin and write his name, student, on the check, and put this check in the box. Okay, in 5 years nobody will know that it was Martin who should get these 500 coins. Okay, so he's cheating. Well, the bank in few years noticed that, because people started to argue, etc., and they do some audit and they see that this student was cheating. So what they do is they employ one auditor, and this auditor, what he does is he prevents the student to seal the box and the block these transactions. He checks if he didn't cheat anything. Okay, well, now the system is not so perfect anymore, because this bank has to employ more people, and by employing more people it's slower, and also they have to pay more, because they are paying now a clerk or an auditor who actually has to have more money. But they do that. But after 1 year, even this clerk, because he's paid very, very little, and his wife left him, and now he has to pay alimony and doesn't have any money, he thinks about the thing that nobody knows where they are, he and the student. Nobody checks what they are doing. So he tells the student, well, listen, if you are going to cheat for one transaction, I'm going to be silent if you cheat for the other transaction for me. Okay, so they are interchangeably cheating and cheating. But after some time, the bank realizes. And what does the bank as an answer have? Well, the bank introduces another system. The bank introduces another room, you see, another room, another student, another auditor. Because what's the idea of the bank? Well, the bank said, well, guys are gonna be bad, okay? And they produce a box where the other 2 guys won't be in the other room. They are good. And they will see that if this box is different as this box, well, they will notice that those two were cheating. However, how can the bank now be sure that this box is really the same as this box? If the bank wants to ensure to easily check on them, they will have to ensure that each box here is pretty much equal as the box in the other room. And how can the bank ensure this? Well, the bank comes with a solution. The bank says, well, I'm going to employ two other guys. However, now they all have to use the same principle, weighting these transactions. But the one who is faster, and please look at here, the guys in the room 1 were faster than the guys in the second run. What they will do is, in this case, when they finish finding the correct solution, they will call this middleman, this post guy, give him this block of code, and this block of code holds information which transactions are in this box and how many cents of grain are in this box. And this guy will bring this information to those other guys. Well, this student will say, no, he wasn't, he was cheating. The first student was pretty much cheating, he cannot be faster than me. Well, the postman says to him, I don't know anything, here's the recipe. Well, this sheet of paper holds the recipe how to check if this one was sincere. What he will do is, he will read which transactions the previous student took, put these transactions on the weight, put so many grains as the previous student put on it, and he will come to the solution 1.1000. In this way, this student in room 2 will be sure that student in number 1 has done job correctly. He will be able to prove his work, proof of work. Okay, and in this way, since he had to prove his work, this student in room number 2 was also actually sealing the same box. So in this case, the bank has a solution that both rooms will have the same boxes, and the bank will also say that every time one of them is faster than the other, he will get a bonus. He will get 25 coins more at the end of the month. Okay, but at the end of the day, since we have a connection between them, this guy thinks, well, since he fell down while driving and the bank didn't want to pay him any insurance money, he tells to these guys, well, look, if you are gonna cheat and I'm gonna convince the other guys that they will cheat, well, we all gonna cheat and the bank will not notice. But after they do that, they start to do cheating. But after a few years, the bank will notice that, because the truth comes always to the light, and the bank comes to another solution, and a stupid maybe one, but it's not really so much stupid, because the bank employs another room number 3, employs another student, another auditor, and they all compete with each other. And when now this student solves the puzzle, and in this case the puzzle is putting so many transactions in the box and finding the right number of grains, when he finishes the first, he sends this guy to other 2 guys. They both can check that the first student has done the job. Both seal the same box. And maybe the next time he will be the winner and he will just copy the same thing. And in this case, we have a distributed system. We have a peer-to-peer system. We have a proof of work. Okay, we have a mechanism to ensure proof of work, and we have a mechanism to ensure only one truth, because now this is the solution that everybody is pretty much really distributed and decentralized. Okay, and this is called mining. But why is this called mining? How much time do I still have left? I have 20 minutes left. I will explain to you in a minute or so. But what is important is that you guess the analogy of this. These rooms and these boxes and these students, they were miners, blockchain miners. And what were they doing? They were actually having these transactions, and each of these boxes actually is a block of transactions. And each block of transaction has this information. It has a transaction list, So each box has different transactions and has a nonce. So what is a nonce? I'm gonna try to be fast as possible. SHA-256 generator. You should probably see my screen. So I'm sorry, I don't hear you. Hello? So I didn't hear you. Did something wrote or? Okay, I'm gonna continue. We have, let's say, a transaction 1, transaction 2 in the box, transaction 3 in the box. So at the sense, the students were looking for grains of sand to come to the 1.000 milligrams. In computer and in blockchain sense, what mining actually means is that the miners, these nodes, these computers in the peer-to-peer networks, they have to seal these transactions. Let's say we have 4 transactions and they have to seal them in a box, and this box has to be 1 megabyte of size. But the idea is that, as you see here, when you put these transactions into this box, at the end you are calculating a hash functions. Note that when I put something new in the box, we are actually changing the hash functions. The idea to come to the 1.000 milligrams is actually, in mining sense, in blockchain, that you have to produce such an input field, such a box, which will hold such a hash functions that will have 1 0 in front. So if I can put only, you see here, 8 transactions, 7 transactions in it, how can I produce a hash with a 0 in front of it? And these transactions can be, for example, Alice sent Bob 1 Bitcoin. Bob sent Alice 1 Bitcoin back. You have sent me 1 Bitcoin, etc. These are transactions. And they have to be sealed in a box. But this box has to have a hash value of a 0 in front of it. How can I produce a hash value in front of it if I cannot control the output of a hash value? Well, I can randomly try to put it a nonce. So what I'm actually right now doing is trying to guess a number which will produce a 0 in front of it. And I can do this maybe 1 hour, 2 hours, or whole day. Oh, and this is it. So as you see here, I had to produce this number. I had to input this number beside these transactions to come to a hash value which has a 0 in front of it. Okay? So that's what these students were actually also doing. And why is this called mining? Exactly because of this manner, because I'm actually mining for a number which will produce a 0 in front of it. Okay, so that's the purpose of mining. That's why this generates so much money. But in public networks, there's so much to talk more about these things, which I don't have time. So I will try to maybe show you something else. Also to explain something else. First of all, what I have introduced to you now is the concept of blocks. Well, blockchain transactions, if I go back now, when you produce a blockchain transaction, and this blockchain transaction can be that Alice has sent Bob 5 Bitcoins. Well, when Alice does that, she produces such a transactions, and she will sign in this transaction using her private key, and she will distribute this transaction to one of the nodes, to one of the computers. Other computers will distribute and replicate these transactions to all others, and now these computers in this peer-to-peer network will compete between each other to store this information and transaction in a box. And when once a box is sealed, it can never be changed again, because a lot of other things are also important. However, this only applies when we have these public blockchain networks. We do not have to have public blockchain networks. And public blockchain networks, they are only meant for specific cases. We can have private blockchain networks. These are public. Cryptocurrencies are based on public networks. And if you have a public network, everybody can join this network and everybody can leave this network. And since it's purely decentralized, you have to have a mechanism to have the one truth. And the only way to ensure 100% sure one truth is by enforcing mining. But if you do not have to be bound to public networks, if you create your own network of semi-trusted authorities, then you don't have to have proof of work and you don't have to mine. You can use proof of stake, proof of authority, etc. And in this case, what we have done in the EduCTix network is, I'm gonna just try to explain it to here. We have universities, University of Maribor, Technical University of Brno. We have Bielefeld Hochschule, Germany, okay? We have also Croatia, Sveučilište Zagrebu, Croatia, okay? We have also Tehnički Univerzitet Sarajevo in Bosnia, okay? So what we have done is we have connected these, and I will use this opportunity to thank university to participate in this project and this network. We have connected these universities in a blockchain network. Since this is a consortium network, it doesn't have to be public because somehow we trust each other. We trust that the Technical University of Brno will not cheat. Technical University of Brno will trust us that we do not cheat, etc. So the idea is that each of these nodes of our universities, we all have these databases, okay? And they are replicated, as you now know. Well, the idea is that this is a blockchain network. And when now, let's gonna say, when now Brno gives a diploma to a student of yours, okay, it creates a JSON file, okay? This JSON file holds all the information about the student, who he is, what diploma he earned, etc. And now Technical University of Brno sends this information to the blockchain network. Suddenly, all other universities will hold the same information, the same JSON file at their space. And when, for example, this student will come to Erasmus to our university, he will not have to bring any information with him. University of Maribor will already have this information, and University of Maribor will be sure that this information which was produced by Technical University of Brno is trustworthy. Why? Because this transaction was signed by Technical University of Brno's information. Okay, so I'm gonna just demonstrate to you how this is actually working. And we have this EduCTix network. It's working on the blockchain network that I explained you. I have to log in using my credentials. And as you see here, I'm now logged in with this student's ID. I'm a student 737-04552. Okay, so this is me, and I'm controlling my identity using this digital wallet. This digital wallet, as you see here, it's an online, it's a Chrome extension called MetaMask. It controls my private and public key of the student. Okay, and if I go here, and I copy this information, okay, I can also switch because I have multiple accounts on it, and I'm gonna switch. And as you see here, I'm connected to this EduCTix blockchain network. I could also be connected to Ethereum public network or any other, but I'm connected to our network between our universities. And I will now change my account to my professor's account. And as you see here, it already notifies and knows, this platform knows that I am now University of Maribor, a certified institution. And I can issue a new certificate. And I'm gonna issue a new certificate to, let's say, diploma, unit ID, some achievement, let's say database 2 course, some description, course type, let's say it can be 10 ECTS points, it can have a link, University of Maribor, and I am sending this to this student with this ID, okay? His internal student ID, I don't know, our internal IDs are such as this, and let's say it's Yanis Novak. And when I say issue this, the system asks me, do I confirm this transaction? I can read it and I say issue. What you will see now is, you see, this wallet, which controls my private and public key, opened this. And now it wants me to confirm. And when I say I'm confirming this, I'm actually signing this transaction using my private key. And as you see here, transaction 5 confirmed. What does now this mean is that if I now log in back as the student 7370455 and I go to my received certificates, I see here I have already 4 certificates. If I want to open them, I can go here. Oops, sorry. Just a moment. This is account detail. Let's put private key. I want to open this. You see, I will decrypt this information. And as you see here, I have all of these diplomas in it. And as you see here, database 2, previously published, and I can open these certificates. And what I can do now is I can export this certificate, database 2. And please, as you see, I have exported a zip file. When I open this zip file, I'm really rushing because I only have 2 minutes or 3, sorry for that. I have 2 things in this zip file. I have a PDF, which was generated by the system. It looks something like this. EduCTix, Yanis Novak, passed the course of database 2, blah, blah, blah. But it has also a JSON file. And when I open this JSON file, Notepad, I'm just gonna show you. It's just data in it. Computer readable data. You see, blah, 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 database 2, etc. And let's say I'm gonna change something. Let's say I'm gonna change the value to 11 and store this back. I'm cheating now, okay? But don't tell it. I'm gonna say really true one. Okay, and now I'm gonna send this information to a company. Let's say I want to be employed at SAP in Germany, and I send them this information. Well, what SAP can do is SAP can use this received information by the student, go to platform.eductix.org, drag and drop this zip file, and when they drag and drop the zip file, well, they see that the certificate is not valid. Okay, and they see that I have cheated. But if I use my original one and I drag and drop, oops, and when I drag and drop it again, the one that I didn't cheat on, well, it's legit. And SAP can now believe that all the information that's stored in this JSON file, and they can open it using some APIs of their own, is legit. And they can also verify that this information in this transaction was signed by University of Maribor or Technical University of Brno. And they don't need to call our universities to say, hey, did you really store, or did this student really got this diploma or not, etc. And this is probably the most chaotic presentation. Demonstration for you, but sorry, it was as such because of the time limitations. So I hope it was interesting. If you have any questions, please.
Yeah, thank you. Thank you very much. I can see the echo and so it. So just let me stop sharing. So it's better, hopefully now. So thank you, Mohammed, very much for your lecture and explaining how blockchain work, and at the end how we can actually use this great technology for transfer the data about the students. I just checked the chat, and I'm not sure if all the participants can see and write down the questions. So now I would like to open this question answer session. So if there is someone who would like to ask the question, please go ahead, directly unmute your microphone or raise your hand, and you can ask a question directly. Okay, if the participants are still thinking, I would like to ask you. So I'm just thinking that's a great. However, there are a lot of universities when we are speaking about European space, and I was thinking about the data, because we know that the data are really sensitive, and you're thinking about the security. You have mentioned as well. So when a SAP would like to check my diploma, the content of the diploma, so it means that as well these companies will be joining the blockchain. How we will secure the data of the students? We share with the others, with those who are in the blockchain.
Yeah, I heard two possible questions, and I'm going to try to answer both of them. First of all, or maybe even three: data privacy and data security. Of course, the idea is that if University of Maribor would store this JSON file as a pure transaction in this blockchain, then all of the universities, in this case also Technical University of Brno and all the other universities, would be able to read the pure data. In this case, the privacy of if I would be a student, would be violated. And in this case, University of Maribor would have to pay a fine because of the GDPR, because it transferred my private data to other universities, even though I didn't want it to. Mm-hmm. So how we solve this is that we use the blockchain as the generator of the truth. So when the universities, they create these micro-credentials in the form of JSON files, what they do is they encrypt this information, hash this information, and put the hash of the value on the blockchain. And that's why, as you recall, even if I was the student, if I wanted to read this information from the blockchain, I had to write down my private key. And when I wrote my private key, I was able to see my diplomas. And when I saw my diplomas, I could send them to anybody else, but a zip file. And if the receiver of this zip file believes me, he won't have to need to check it. But if he wants to be able to see if this information is really legit, he can use the platform, upload this zip file, and what the platform does is encrypts the message, and checks if this encrypted file and the hash of it is the same as that one which is stored on the blockchain. And this information is shared between the universities. So the user and the student controls who sees the data, while universities are able to verify data that are exchanged between them.
So actually it means that all of the students, they will possess their key. So nowadays they do have some kind of ID, and maybe it can be connected with their key, which will be generated, and actually they are owners of their own data. So if they send, if I just correct me if I'm wrong, so they actually, when they send the information, they send it and use it to those just whom they would like to send. So they actually got the control about the flows of the data. So not all the participants of the blockchain, not all the members of the blockchain has got automatically approached the data of those who are in the blockchain. Okay.
Correct.
I'm sorry, I'm not IT, so my background is in the management and.
No problem. All the participants of the blockchain can access the data, meaning all universities can access the data, but access is not same as read the data. They can access the data, but they cannot read it because it's encrypted. So the only one who can encrypt the data is the student. He can use his keys to show and decrypt these data. So that's the idea behind it. However, if the students and the universities want to use this platform, they will have to actually enable, each student has to have these digital wallets, as I showed you. It's an add-on in the Chrome. And he has, by having this digital wallet, he actually creates this private and public keys. Okay. This could also be achieved using these qualified electronic certificates that you get from your government, probably. In Slovenia, we call them Sigenca, but I guess all countries have some form of qualified electronic signatures and certificates. And this is implemented also in this case. And the project that you mentioned at the beginning, which I'm the coordinator at our university, Digital Europe for All, is a Horizon 2020 project, Europe's project. What we are actually doing in this project with various countries like Holland, Spain, and many other countries, well, we are actually trying to solve this problem. That this is enabled by using classical means, and these classical means are these qualified electronic certificates that countries have. And in European Union, we have the eIDAS scheme, where we actually now are able to verify, Slovenians can now verify your digital qualified digital electronic signatures, and you are able to verify my own, etc. So.
I get it. Okay, thank you. So you see, you now work and introduce this to the European Commission. So do you think that in the short or longer time there will be the way which will be supported by the European Commission to implement it in the universities, in the public institutions?
Unfortunately, I didn't have time to explain because the title of my presentation was also verifiable credentials. I didn't even come to this part. This is my problem. But yes, European Union has the CEF building block. It's the Central European, I forgot what the abbreviation actually stands for, but there's under the CEF, there's the EPSI, European Blockchain Service Infrastructure. And the European Commission is actually already building a blockchain infrastructure between member states. And I don't know how familiar you are with the eIDAS network, where each country has an eIDAS node, which is responsible to verifying their citizens' qualified electronic signatures and verifying from other European unions. The same is now being set up in the European Union, where you will have member state blockchain nodes. Each country will have a blockchain nodes, and each citizen will probably get his own verifiable ID. And this verifiable ID is, in pretty much similar words, if I say a JSON file holding your information, digitally signed by your government, and you can use this one, and the hash of it is already stored on this European-wide blockchain network. And using these JSON files, you will be able then to interchange various information, sign this information, etc., etc. So yes, it is being built by the European Commission. In some cases, our laboratory is, through these projects, also participating and helping them.
Okay, so I'm sorry, I know that you are in a hurry. However, there is one question on chat from Wojciech, and his question is, isn't the peer-to-peer network problem its speed? So the speed on the peer-to-peer network.
Yes, well, you always, in computer science terms, we always have this trade-off between security and availability. And it's the same as in distributed databases. You can replicate them or shard them. You have these ACID principles and NoSQL databases, which rely on basically available. They are tended to provide speed. But in peer-to-peer network, distributing data comes always with latency. Okay, you want to ensure low latency as much as possible and high throughput, but this is not possible if you have a huge network, a public network. And you have to note that, for example, Ethereum or Bitcoins, these are public networks, everybody can join them. They are actually holding now, there are probably like 5,000, minimum 5,000 nodes, or in some point there were already 50,000 Ethereum blockchain nodes, meaning 50,000 computers were connected to each other in a peer-to-peer network. And when I now send one information, and this information has to get to all of the other 49,999 computers, even if the internet is fast nowadays, it will still take time. And because this takes time, these ledgers will actually produce side ledgers, and we will produce these orphan blocks. And these orphan blocks mean that one partition of the networks will have one ledger because additional information was not available at that time for this part of the ledger, but other network will have another partition. But these blockchain protocols, they have a mechanism to solve these partition problems because they are called fault tolerant. They are Byzantine and crash tolerant. This means that these protocols by themselves have mechanisms that even if information is not immediately at the other point in that partition, that at some time eventually this information would get there. It's hard to explain it easier than this. It is a problem, I agree, but there are mechanisms that solve this problematic.
So I can hear again the echo, so someone's got the micros on. Thank you very much. So if there are no more questions, thank you. Oh yeah, Thierry, please go ahead. Yeah, it's time for maybe if Mohammed allows, so then for one question, so very last question, please go ahead.
Just one short last question, which is a little bit connected to the one Stenka already asked. I wanted to generalize a little bit before she asked. And for me, it seems, I know I'm not an IT guy, but I've heard of blockchain as the encryptic system, as you said in the beginning, the new millennium system. It seems in your presentation, but maybe I don't know enough about it, that there are no limitations. And as we know as researchers, there are always limitations. So for me, at the moment, it sounds that it is the solution and the system which has really there are no bugs, there are no things which can, I don't know, we are talking about quantum computers, what could be a possible threat to the system, but it seems as it has solution for everything. So can you please say something about limitations maybe?
Thierry, perfect question, and I like that you think as a researcher, you always have to ask, there's a rabbit in the wall, yeah. Nothing is perfect, and I'm sorry if it sounded as a perfect solution. It's not even near to a perfect solution, not even near. There's so many challenges with blockchain technology, and because we have so many challenges, there was one big problem that in 2017, the whole world, meaning people in taxi drivers, my grandmother, people all around the world who don't know the basics about computer science. They were talking about bitcoins, and because of this value of it, etc., and people got rich of it. And after that, it broke down, and nobody trusts now blockchain, except some enthusiasts. Blockchain as a technology, it has many challenges. One of the challenges is scalability, and it is really hard when you're replicating things. You're always just replicating, meaning if I put some information, take for example, if University of Maribor would put now the whole history of our students into the blockchain, immediately this information would be replicated at your university. Meaning suddenly 50 gigabytes of data would jump also at your university. If you need it or not, you will have to have it. Okay, and scalability is one of the problems you raise with memory, etc. Then one other problem is also security. Then other problem is, for example, quantum cryptography. Even if we use elliptic curve cryptography, even that is vulnerable to quantum cryptography. But quantum cryptography is still like 10 years impossible real usage, and they are, for all of these challenges, we have possible solutions. So if you are a researcher in computer science today, this is a great field because you have so many things to do, you will never sleep, and this is good. But there are a lot of limitations. Security, scalability, and many more identity related challenges and limitations. Because as you see, I have used this MetaMask, and this MetaMask is enforcing our students in University of Maribor to have additional digital identity. But because we have to use blockchain, and blockchain is not enabled us to use qualified electronic signatures, so meaning the student has to now have a digital wallet, plus the government-based credentials, plus maybe university credentials, and there are a lot of challenges that still have to be dealt with.
Okay, thank you.
So, thank you for answering this very last question. And yeah, thank you for your time, Mohammed. Yeah, I hope that the time allows us. So you can see behind me the picture of the Brno city, and I would like that you can come and visit us, because some of our colleagues already were in Maribor, our IT guys, and they referred about this platform, and I have heard as well from Bielefeld. Yes, it would be great if you can come and maybe share this idea, which, as you have said, there's got limitation. However, it's one of the options how we can work and share data in the future. So thank you again. If you would like, you've got a program, and if you are interested in some of other lectures during this International Week, you are cordially welcome to attend the lectures of other participants. So, a lot of greetings from Brno, and hopefully the situation allows us, and we can meet each other as well in person. So, thank you.
Thank you very much. Thank all of you for the questions. I hope it was useful, and I hope we see each other maybe soon also live. So have a nice day in Brno, and bye.
Bye. Have a nice rest of the day. Bye. Thank you all.